First of all, I would like to thank the organizers for giving me an opportunity to present this research here today. So this is the title page of this talk. This talk consists of 3 parts. The largest of them is devoted to a new approximation.
Can you use the microphone? Can't hear you. I can't hear.
Can't hear.
How do I turn on? Thank you. So the largest part is devoted to a new approximation free theory for stochastic differential equations. This theory is important from the point of view of fundamental knowledge in mathematical physics and other sciences. In particular, it provides a unified mathematical framework for and the rigorous definition for such basic concepts as thermodynamic equilibrium, dynamical chaos, or other stochastic generalization of that concept, which did not exist before, ergodicity, and so forth. It explains what is the mathematical essence of ubiquitous chaotic long-range order in nature that reveals itself through such well-established concepts and phenomena as 1/f noise, butterfly effect, power law statistics of avalanche-type processes, which is basically the reason why a Richter scale for earthquakes is logarithmic. It also provides the classification of stochastic dynamical systems, very general classification. And it is still work in progress, but it already has something to say about neurodynamics, and that will be the last part of this talk. But before I get to those issues, I would like to discuss briefly that part of dynamics and brain that I think this theory is going to be most useful for. So it is experimentally well established and accepted picture that dynamics and brain can be qualitatively or roughly separated into 2 major parts. The first part is neuroplasticity. It is a relatively slow reconfiguration in neuronal network, changes of the primaries of synapses. It can also be called neuromorphics. It is responsible for long-term memory, and the other part is the dynamics of electrochemical potential from neurons and synapses. To separate it from neuromorphics, we can call it neurodynamics for brevity. And this part of dynamics and brain is responsible for short-term memory, probably consciousness and others. And the experimental evidence that such a separation can be done is the fact that anesthesia that suppresses the neuron firing disrupts the short-term memory, consciousness, obviously, otherwise it wouldn't be anesthesia, and it does little to the long-term memory. And whatever it does, it can always be blamed on the interaction between neurodynamics and neuromorphics. It is understood that neurodynamics and neuromorphics, they overlap on a temporal scale. They interact non-trivially, otherwise we wouldn't be able to learn in the long term. And one of the interaction mechanisms, there are probably more, I'm sure there are more. One of them is the long-term potentiation. It's basically a sudden change in the synaptic strength initiated by recent neurodynamic activity on it. So the whole picture, information flow, is because of that interaction between these 2 major types of dynamics and brain is quite complicated. Probably roughly can be described as information from environment goes through senses in the form of electric pulses, goes into neurodynamics, it does whatever it does, and then it goes into neuromorphics. On the side of computational paradigms, neuromorphics is understood to a certain degree. The whole science of neuromorphic computing is based on it. To the best of my knowledge, qualitative understanding of neurodynamics does not exist yet, or rather, neurodynamics exists on the level of computer simulations of evolution on neuronal network. There is one simplifying feature in dynamics and brain. This stems from scale separation. The point is that the short-term memory or neurodynamical memory is on the order of minutes, maybe dozens of minutes, whereas long-term memory can last a lifetime. And the reason for it is the different physical implementation of these 2 types of dynamics, because neurodynamics involves electromagnetic interaction, and it's very fast and long-ranged. As a result of this scale separation, the adiabatic approximation is applicable. In other words, we can assume that neuromorphic configuration of brain is stationary, and to see what neurodynamics does, it is a reasonable assumption to think that qualitatively neurodynamics will not be changed. Such a brain will not be able to learn in the long term, of course, but whatever it does can be studied within this approximation. Probably the best example of adiabatic approximation is the Borne Oppenheimer approximation for molecules that consist of heavy and slow nucleus and fast and light electrons. In this case, you can believe that nucleus are fixed in space, solve for Schrödinger equation for electrons, and use the ground state energy as the effective interaction between nucleus. So within this approximation, one of the possible models for new dynamics is just some stochastic differential equation. It can as well be some coupled HH elements. And we can also put some environmental term that comes from the environment to probe the system, and there's always, of course, noise that represents variables that we do not track. And it is already on this level, it becomes clear that neurodynamical or short-term memory is dynamical in nature. It means that whatever influence from environment comes is recorded not in a majorly recorded in the change of the trajectory in the phase space. And the best dynamical memory is, of course, chaotic. It's known as also as a butterfly effect. Does it mean that neurodynamics is chaotic? And getting a little bit ahead, the answer is yes and no. The point is that the brain is basically on the border of chaos. It's in the phase that I prefer to call intermittent. But I believe the main idea of this slide is to just to make a statement that neurodynamics is a stochastic differential equation. If we want to study it, we have to make sure that we understand stochastic differential equations to a good enough level. And previous theories of stochastic differential equations, they provided many important insights. Nevertheless, many of the very important questions remain unanswered. For example, there was no definition of dynamical chaos for stochastic case. There was no explanation of the chaotic long-range order. Even on a very low technical level, there was no agreement among mathematicians on the form of the correct form of the Fokker-Planck operator. This disagreement is known as Ito-Stratanovich dilemma. So the theory that I'm going to turn to now gives the answers to these questions and other actual questions too. So, as I said, it's very general. It is applicable to all continuous time dynamical systems. Because of the stochasticity, it is probabilistic, and it can be also compared to another probabilistic theory in modern physics called quantum theory. It actually applied to only a subclass of continuous time dynamical systems that corresponds to classical mechanics or the distraction principle. So that emphasizes the generality of it. So I'll be talking about this class of stochastic differential equations. All possible generalizations are possible. It can be, the noise can be anything. It can be partial differential equations. The flow cannot be necessarily local in time, space. And but this equation covers most of the models that can be found in the literature. And a few objects there. One of them is what I call Weinbeins, because they define the noise-induced metric on the phase space. And in case if they are dependent on the position on the phase space, the noise is called multiplicative. If they are independent, it's called additive. So how to derive the Fokker-Planck evolution for density probability distributions? We first note that stochastic differential equation for a fixed configuration of noise defines a map of the phase space onto itself. It can be visualized as trajectory, so you have initial point and it goes somewhere in the final point. These maps, they induced actions on generalized probability distributions. These actions are known as pullbacks. Pullbacks are linear operators on infinite dimensional linear spaces, so the operation of stochastic averaging is well defined, and once that is done, the infinitesimal version of stochastic evolution operator is the generalized Fokker-Planck equation. The Fokker-Planck operator consists of two parts. The first one comes from the flow vector field, as they call it. This first term in the stochastic differential equation. This term is d, or physical derivative. It represents the average flow of the density along the flow vector field. And the other one is the noise-induced diffusion. This term is a member of the family of Laplace operators. And its leading term looks like this. It couples to a metric, and metric is the square of those Vellbanes that appear in the stochastic differential equation. That's why they call it this way. So there are no approximations made in this derivation. And in particular, it solves Ito-Stratanovich dilemma. It turns out that if you apply this operator to top differential form, which represents a total probability distribution, then it takes the form of Stratanovich-Fokker-Planck equation. It can also be shown that Stratanovich approach is equivalent to the so-called Weil quantization of symmetrization of operators when you come from path integral representation to operator representation. And speaking of generalized probability distributions from a mathematical point of view, they are elements of exterior algebra. They are differential forms of all possible degrees. The differential forms, they represent volumes, differential volumes in the phase space. So the so-called top differential form that has all the differentials in it is the total probability distribution. If this form is a lower degree, then it might be interpreted as, for example, as conditional probability distribution. One may wonder why we need those objects, and it turns out that we really need them, especially for chaotic dynamics, when the ground state is not the total probability distribution, but the conditional probability distribution. And that these objects carry their differentials with them makes them actually coordinate-free objects. So basically, they do not depend on coordinates that you introduce into the phase space, because it's actually in your head. And these ones are invariant. And so Fokker-Planck operator can be given this form on top. It's explicitly supersymmetric form. This form of Hamiltonian is unique to a class of models in high-energy physics known as Witten-type topological field theories. A subclass of that is known as supersymmetric quantum mechanics, for example. This form in particular suggests that the Fokker-Planck operator is commutative with this d, where d is the exterior derivative. And this means that d is actually a symmetry, a supersymmetry of stochastic dynamics. This also suggests that all the eigenstates of the Fokker-Planck operator are divided into supersymmetric singlets, non-trivial Derive cohomology, as they call it, and the non-supersymmetric pairs of boson-fermionic doublets, as they call it. It also suggests that all supersymmetric eigenstates have zero eigenvalue. And the meaning of this D operator is basically the algebraic representation of the concept of boundary. It is the matter of the Stokes theorem that relates the integration of the volume to the integration over the surface. And there is also a concept of Poincare duals of submanifolds. And on these objects, this operator acts as the boundary operator would have acted on the original submanifold. And what it means that it commutes with evolution operator is that you can take the boundary before you evolve or vice versa. And the result is the same. And speaking of the eigensystem of the Fokker-Planck operator, so it is real. It means that all the eigenstates are either real or common complex conjugate pairs. These pairs have its predecessors in dynamical systems theory known as Roulier-Polyakov resonances. So all supersymmetric states have zero eigenvalues, I already said. And what is also important, that there has always existed at least one supersymmetric state of steady-state total probability distribution. The state can be called the state of thermodynamic equilibrium. So all these properties reduce possible spectra of Fokker-Planck operator into free, qualitatively different forms. And this red dot there indicates the ground state of the system. It's basically the state where the system goes after infinitely long evolution. So the second and the third correspond to spontaneously broken topological supersymmetry because the ground state is not supersymmetric anymore. There are also theorems from dynamical system theory that state that evolution operators, they call it transfer operators, they have real ground state. So probably the third one may not be realizable. But but when it is, it will have yet another important feature that the time reversal symmetry there is also going to be broken because among the two Roulet particle resonances, you have to choose one as a ground state. But we will not talk about this possibility. So basically, we have two types of spectra. The first one, unbroken topological supersymmetry, corresponds to thermodynamic equilibrium. The ground state is a steady state probability distribution in the phase space. The other one is spontaneously broken symmetry. The partition function, which represents the stochastic average of the periodic solution, grows exponentially with time. Such behavior is known sometimes as dynamical complexity. It is related, the eigenvalue of the ground state is related to some such concepts as topological entropy in dynamical system theory and so forth. And this feature is actually unique to chaotic behavior. This is basically the proof that spontaneous breakdown of D-symmetry is the stochastic generalization of chaos. There are two major objects in the theory that have like the partition function type of looks. One of them is the Witten index. The other one is the partition function already mentioned. The Witten index is topological in its nature that actually represents stochastic partition function of the stochastic noise. That's why it doesn't depend on time and many other things. For closed phase spaces, it actually equals the Euler characteristic. And if we look at these two major objects, we understand that the previous invention, or rather something that we thought was invention, that we have to consider wave functions that are not total probability distributions, but differential forms of lesser degree, is actually a necessity. Because without this, Witten index wouldn't exist at all. On the other hand, we understand that the partition function of the noise is an important thing. It's got to be somehow represented in the theory. And the partition function itself is either will not represent the number of periodic solutions, which is also not good. And in the path integral language, these two objects respond to periodic boundary conditions for fermionic fields and anti-periodic boundary conditions. So this path integral representation actually corresponds to the so-called Parisi-Surlas stochastic quantization procedure that directly leads to that object. So speaking of the ground states, in the deterministic limit, they represent the so-called Poincare duals of global unstable manifolds on the phase space. And in case the system is not chaotic, those manifolds and the ground states are well defined. In case when it's chaotic, those manifolds are not topological manifolds. They can fold on themselves in a recursive manner. And one of the textbook examples of the homoclinic tangle, given at the bottom of the slide. So if you try to construct a Poincare dual of such a global unstable manifold, you will see that this wave function does not give you zero when you act on it by this supersymmetry operator, means that the supersymmetry is broken. And when you go to stochastic case from the deterministic limit, one of the ways to interpret the idea of supersymmetry breaking in this case is that the bra and ket that actually represent stable and unstable variables in the system, they are stochastically independent, or in case of unbroken symmetry. And if it is broken, then they are not stochastically independent from each other. And this last slide, theory slide, is basically the proof that if your supersymmetry is spontaneously broken, then your system will have infinitely long memory of perturbations. So what you can do is you can take the flow vector field and add those probing fields in there as though you can control them, and then see how it responds, how the partition function changes if you start manipulating the system. So if the system has unbroken symmetry, all of these correlators that represent the response of the system, and the long time limit I0. It means it doesn't remember the perturbations, but if it was broken, it will remember. This is the stochastic generalization, the famous butterfly effect, that previously was thought to be a part of the definition of dynamical chaos. From this point of view, it's actually a consequence. It's one way to explain the famous Goldstone theorem that says that if a continuous global symmetry is spontaneously broken, then one has long-range correlations in there. And so intermediate result is that all stochastic differential equations are divided into two major parts. The one with spontaneously broken topological supersymmetry has infinite memory. Its ground state is not a total probability distribution. And in particular, statistical approaches to this system may not be quite applicable, or rather they will provide a reduced description that does not capture the most important part of this long-term memory in there. And we can actually go one step further in the classification of the systems. This classification comes from the analysis of how the supersymmetry can be broken. In high-energy physics models, there are basically three levels that can break a symmetry. It's a tree level, then perturbative level, also called anomaly, and the instanton or anti-instanton condensation. And in our case, this instanton condensation means the condensation of noise-induced tunneling matrix elements. And now if we call that Fokker-Planck operator is dominated by Laplacian in a high temperature limit, then the conclusion is that as we increase the temperature, the supersymmetry will eventually get restored, and this limits all the possible phase diagrams into two different types. The first one is not very interesting. It was so basically at zero temperature it's broken by non-integrability of the chaotic flow vector field, and then it just gradually disappears. But the second one is more interesting. So what happens there is that there is a region in the phase space where the system is chaotic, but this chaos can be identified as a noise-induced chaos. So if you shut down the noise, the system will cease to be chaotic. And what is also important here is that for a high temperature limit, these concepts of noise-induced tunneling, for example, between different attractors, they are hard to tell one from the other. It means that the boundary between ordinary chaotic and this noise-induced chaos that I call intermittent must smear out into a crossover, and two phases must mix into a complicated phase. Probably a good name for it would be a chaos and strong coupling limit. And this is pretty much all on the theory side of this story. And let me now turn to the last part of this talk. It's the application of what we know from theory to neurodynamics. So experimental studies show that neuroavalanches, which are actually neurodynamical instantons, they exhibit powerless statistics. And this means that the brain is actually in intermittent phase. And there are also numerical studies that show the same result. From the point of view theory we discussed before, we can make the following conclusion, that if an experimentalist can tell neuroavalanches, it means that this is a low temperature regime, and it means that there are only three possibilities. It is either chaotic or intermittent or thermodynamic equilibrium. Now, the conscious brain cannot be in a thermodynamic equilibrium because that phase does not have memory. And the chaotic phase can be ruled out by qualitative argumentation that chaos most probably must be associated with a neurodynamical phenomenon of seizure. Basically, when neuroavalanches, they overlap in spatial temporal scale, and they basically run as one. And so this is like a logical proof that the conscious brain must be an intermittent regime. What is important here from theoretical point of view is that conventional dynamical system theory or a theory of ordinary differential equations will cease to explain this phase because it this phase disappears as you shut the noise down. And it is certainly true that intermittent phase for neurodynamics must have a fine structure, like being awake and being asleep. In sleeping, certainly qualities are different, but at this level it will not show up. Maybe it may show up on the level of low energy effective theory that I would like to discuss briefly next. So yesterday there was a discussion regarding whether we have to track all the variables in the brain or it is sufficient to consider only important ones. Actually, it is a modern physical paradigm that all elementary interactions, they are actually effective field theories. From some theory, some people call it theory of everything that probably physicists don't know yet. Previously they believed it might be a string theory, but not anymore. And this is a typical situation for symmetry breaking phenomena. A few more examples is, let's say, in ferromagnet, the important dynamics is actually not in all the electrons, but only an important parameter, which in this case is the local magnetization, and the theory for its dynamics is known as Landau-Lifshitz-Gilbert theory. In case of superconductors, the other parameter or important variables is basically the wave function of Bose condensate of Cooper pairs. The theory of elasticity in solids, it's also effective field theory. It describes, the other parameter is the local displacement of atoms from their stationary positions, and the transverse sound being the Goldstone mode for this symmetry breaking, which in this case is the symmetry of continuous of the movement of the system in space. It's broken down by the lattice structure of the solid. And so the question now is, what would be the important parameters for neurodynamics, and what would be the low energy effective theory for it? And I find it quite fortunate that neurodynamics is intermittent, because anti-instanton condensation is one of the most reliable theoretical mechanisms of supersymmetry breaking in high energy physics models. And it is studied to a certain degree. We can just borrow knowledge from there. Technically, it means that we have to calculate certain matrix elements on noise-induced tunnelings and exponentiate them in the action. The order parameter is going to be a fermionic field, because this is supersymmetry, fermionic symmetry. This field will be gapless because of the Goldstone theorem. This field represents supersymmetric partners of unstable or unthermalized variables in which the system has dynamical memory. And in continuous space models, those variables represent the so-called moduli of solitons. For example, in the boiling water, this is the position of the bubble and the boundary. In case of vortex-mediated turbulence, it's the position of vortices and anti-vortices in there. And this is the relation to continuous space models. But the problem with brain, however, yet another one, is going to be this, that brain is actually a fractal network with multiple connections, and the approximation of continuous space may not be quite applicable in this case, because the coarse graining procedure that is needed to view a brain as a continuous space model applies only to a nearest neighbor coupling. Well, one way around it is to believe that the brain is embedded in a very high dimensional space, like 10,000 dimensional. This may render all the connections nearest neighbor, and then the coarse graining procedure might be useful. But there appears yet another problem, that in such a high dimensional space, there just may not be enough neurons in each direction to think of it as a continuous space model. So this is yet another problem that must be overcome on the way to the reliable low energy effective theory for neurodynamics. And this is the conclusion. So there's a new theory there that explains what is the chaotic long-range order and provides classification, general classification for stochastic dynamical systems. There's an experimental evidence, and there are logical reasons to believe that neurodynamics of a conscious brain is intermittent. It's on the border of chaos and thermodynamic equilibrium. I find it reasonable to believe that the associated long-term memory of neurodynamics must be believed to be the short-term memory in brain. And some qualitative understanding of neurodynamics may appear on the level of the formulation of low-energy effective theory of neurodynamics for important variables, those variables that are unthermalized and have dynamical memory in them. And and this approach will have two stages. Probably in the first stage, the continuous space approximation can be used, and at this stage, maybe some qualitative understanding of possible functionality of neurodynamics may show up, but sooner or later, then this approach must be generalized to operate on the fractal networks of brain is. And I think at this moment that there are reasons to believe that if computational paradigm that is at least distantly related to functionality of neurodynamics already exists, it might as well be topological or fault-tolerant quantum computing. But before all this can be done, many questions must be answered, and in particular on the interpretational basis of the theory. For example, there is no understanding yet what does the external observer do to a wave function, especially in the light that the wave function is a conditional probability distribution. And with this, I would like to thank you for your attention.
So I have one question. I have the microphone. So one of the themes that's kind of appeared in this workshop is on the hardware implementation of neural algorithms and so forth. The hardware is going to add some noise potentially to whatever computation is going on, which I guess is kind of raising the temperature in some respect on your graph. But that noise, the hardware noise is going to have a certain shape, right? Depending, even if it's on conventional, conventional digital computers or analog devices and so forth. How do you think, I don't think you were talking at all about hardware implementations, but how do you think the sort of theory you were developing would incorporate some of the noise characteristics that a hardware implementation would provide?
As I said there, this theory is generalizable to any noise. So I guess your concern is what if the noise is pink? Or what if it's a continuous space model and the noise has non-local characteristic? Or maybe noise is non-Gaussian. All of this will not change the picture qualitatively. But the Fokker, let's say if it's pink, then it means that the Fokker-Planck evolution has to be generalized. Your diffusion operator, this Laplacian operator, must be non-local in time. But it will still possess topological supersymmetry. So this classification of stochastic dynamical systems I believe it will remain.
I have a quick question. Is it possible, since the brain is such a dynamic system, that it's not, these electrodynamics aren't an intermediate short-term phenomenon, but the brain's actually in a continuous state, jumping from one chaotic manifold to another as we think and dream and imagine?
Maybe. One of the possible. Let's say you have different chaotic attractors. So they are chaotic even on the level of no noise. There is a barrier between them. So I think this is one of the types of intermittent. It's not quite intermittent, is it? Because it's already like on the deterministic level, it's going to be chaotic. But the jumps between them will still be detected as an instant on. You can so what you said basically is that you have different chaotic attractors and it jumps from one to that. And I think it may still be classified as intermittent. Even though if you shut down the noise, it's still chaotic. I think, nonlinear science is it's the opposite of linear, right? All possibilities. And It's just a matter of, do we want to think about it as an intermediate or something else? Maybe it's something else.
Okay, thanks.
You are making the connection to objects in physics, condensed matter physics in particular, and I think this is a very important approach that should be followed up upon. But my question is, in contrast to a solid-state physics object, for example, which undergoes phase transition and structural changes, the dynamics of the brain, and we learned that during the last 2 days, is very much, if not only, driven by external inputs. It's not a closed system, not at all. So how are you treating this aspect in your approach?
I think it's a very good question. So what do we consider noise, or what do we consider useful information there? That's basically the way, is that the correct way to reinterpret the question? So basically you have information coming from the environment, and there's also some influence coming from the rest of the body, for example. So what is the noise and what is the important thing? Is that the question?
But I mean, there's highly structured information coming from the environment. I mean, that is what drives the development of the brain.
I don't have the answer to this question, but maybe I have a... My intuition is that one of the functionalities of neurodynamics before it goes to neuromorphics is to filter important information from non-important information. Maybe important information from the environment has some sort of a topological structure.
Okay.
And that will somehow go into neuromorphics. But that's a very long-term goal to understand. At this level, it's impossible to answer.